Okay, so today's experiment, let's zoom in, let's get this set up. Okay, so today's experiment is calorimetry. And the best way I can describe calorimetry is measuring changes in reaction energy by measuring changes in temperature. That's how I think of calorimetry. Now let's talk about the theory behind calorimetry. Let's talk about the theory behind calorimetry. So first and foremost, let's pretend a theoretical example. So let's suppose we have a hot pan. So let's suppose we have a pan that's at 100 degrees Celsius. Let's suppose you're trying to boil some water. Okay? And inside that pan, we're going to put some water at 22 degrees Celsius, room temperature. Now, if we have a hot pan in contact with cold water, what do we know intuitively will happen? What will happen to the water? Will it increase in temperature or decrease in temperature? What will happen to our water if we put it in the hot pan? Will it become at a higher temperature or lower temperature? And don't be shy to type in chat. Yeah, exactly. It's going to increase in temperature. We know this intuitively from our day-to-day life experiences. Now, what's going on in this case is we have a flow of what is known as heat. So heat, quite simply, is energy exchanged as a result of temperature differences. Okay, and energy is transferred from the high temperature object to low temperature objects in thermal contact. Okay. So heat is the energy exchange as the result of temperature differences. So let's do a before and after picture. So heat flows from our hot pan to the cold water. And so after a little bit of time, eventually at the end of this process, we noted that our water will be at a higher temperature, right? So our water is now at, let's just say, 26 degrees Celsius. So it has increased in temperature. And what would we expect to happen to our pan if we put cold water in our pan? Would we expect our pan to still be at 100 degrees Celsius? Would we expect the temperature to increase or decrease? What will happen to our pan if our water ends up warming up as a result of this energy exchange? Yep, exactly. So let's suppose the pan now is also at 26 degrees Celsius. So a critical feature of objects in thermal contact is objects exchange heat until they are at thermal equilibrium. Now, that's a really fancy word, but what it essentially boils down to is that they're at the same temperature. That's it. So objects will exchange heat until they're at the same temperature. Does everyone notice how the water and pan at the end of this process are at the same temperature? And that as a result and that in turn means they're at thermal equilibrium. Okay. Okay, so this is all wonderful. Now let's talk a little bit about what's going on here. And let's use let's invoke some fundamental laws. So the first law of thermodynamics tells us that energy is conserved. What this essentially means is the total energy of a closed, isolated system or let me phrase this another way. It's essentially saying is the total energy of our universe is constant. Don't worry, we're going to tie this back to our example of the pan in a moment. So let's draw out our pan again. Oops. So let's suppose we're back to our pan and water example. Let's draw the pan a little bit. So if we suppose we initially have water at 22 degrees Celsius, and our pan initially is at 100 degrees Celsius, we establish that heat flows from our high temperature to low temperature object. Okay, so if energy is conserved and the total energy of our universe is constant, the heat gained by our water, so any heat gained by our water must be equal. So the heat gained by our water plus the heat lost by our pan, the total energy of our system and the surroundings is going to be zero. So energy is conserved. We have not produced or consumed energy in this transfer process. We've just moved energy from our hot pan to our cold water. Now, as a consequence of this relationship, we can rewrite this expression to say any heat gained by our water must be equal to -1 times the heat lost by our pan. Okay. So we have a relationship between the heat gained by our water and the heat lost by our pan using conservation of energy. Now, we can't easily directly measure heat. However, we can exploit a very useful fact. Objects change in temperature as they gain or lose heat. Okay. So then, we know, so let's think about this intuitively now. So if we have a pan, let's suppose the pan is made of copper solid at 100 degrees Celsius. And let's suppose we have a big block, we have a big volume of water at 100 degrees Celsius. In our experience handling metal objects and handling water, which one of these two objects takes a longer amount of time to cool down? Which one of these objects cools down the fastest? Just intuitively, which one takes the longer amount of time? Or let me phrase this another way. Let me phrase this another way to help us invoke our intuition. So if we have, for example, a copper pan and some water, and we expose it to a flame. So let's suppose we put a flame under both of these two samples. What's going to warm up faster, the metal pan or the water? If I try to heat them, which one warms up more readily? So if you try to heat a sample of metal versus a sample of water, the metal increases in temperature more readily as it gains heat. And the key parameter that we use to describe the relationship between heat and temperature is known as heat capacity, which is given a big symbol C, which has units of joule per gram degree Celsius. And what heat capacity represents, heat capacity is just joule per degree Celsius. And the more useful form of heat capacity is known as specific heat capacity. And specific heat capacity has the symbol C subscript S, has the units joule per gram degree Celsius. And what specific heat capacity describes, in essence, is the energy in joules required to raise the temperature of 1 gram of material by 1 degree Celsius. Okay? So it's a direct relationship between the temperature change of an object and the heat gained by an object. So to help everyone see differences in specific heat, the specific heat of copper is about 0.45 joule per gram degree Celsius, while the specific heat of water is about 4.184 joule per gram degree Celsius. And the key thing I want you to take away from all this is that a large specific heat implies a large amount of heat is needed to raise the temperature of an object. So does that make sense to everyone? The intuitive link, copper increases in temperature more readily when we put it above a flame. Water takes a little bit longer to increase in temperature because it has a larger specific heat. Now, we can relate heat and specific heat. So the heat gained by an object or lost by an object is equal to the specific heat times m, which is the mass, times T final minus T initial, where T final is the final temperature and T initial is the initial temperature of our object. So then, we have a direct relationship between the heat gained or lost by an object and the temperature change. Does that make sense so far? So we are measuring heat gained or lost by an object by measuring temperature. So let's do an example. Let's do an example now, and let's look at a practical example that we'll do in part A of the experiment. So in part A, we are measuring the specific heat of a metal. Okay? So in this experiment, in this first experiment where I measure the specific heat of a metal, we are going to have water at a temperature T initial of approximately 22 degrees Celsius. We are going to take a metal block. We're going to take a metal block and we are going to heat the metal block to an initial temperature of about 100 degrees Celsius. Okay? And then what we're going to do is we're going to drop our metal block into our water. Okay? Now, if we take a little time lapse and we allow some time to pass, eventually, what would we expect to observe? Would we expect the metal, and so if we have our metal and we drop it in the water and we let a large amount of time pass, eventually, will these two objects be at the same or different temperature? Will they be at the same or different temperature? Yep, exactly right, the same temperature. And we'll call this temperature T final. So this is the final temperature of both the metal and the water. Okay. So in terms, the reason why there are two different T initials is because the water and the metal are starting off at different temperatures. Then we mix the water and metal together and we allow them to exchange heat. So the T initial in dark ink is the temperature of our metal block. The T initial in blue is the temperature of our water. You don't have to measure the duration, only the final temperature. Now, if we think a little bit about our map, in a snapshot when our metal block is placed in the water and it has a T initial of around 100 degrees Celsius. Since we have this warm metal block sitting in cold water, is heat going to flow into or out of our metal block? Is heat going to flow into or out of our metal block? Out, exactly. Heat flows from high temperature objects to low temperature objects, exactly. So, from this relationship, we know that the Q of our metal, the heat lost by our metal plus the heat gained by our water, is equal to 0. Energy is conserved. Heat only moves from one object to another. Now, from this, we also know that Q metal, we can write an expression for heat in terms of temperature. So for example, the Q metal is equal to the specific heat of the metal times the mass of the metal times T final minus the T initial of our metal. And this is really important because the initial temperature of each of our objects are going to be different. We also know, and let's use a different color for this. Let's use blue because that matches cognitively with water. So Q water is going to be equal to the specific heat of water times the mass of water times T final minus T initial water. Where did we get this equation from? We got this from our expression of specific heat. All we're doing is saying, what object are we looking at? In this case, we're looking at our metal and our water. Is everyone okay so far? Does everyone understand what we're doing from the pictures? Does everyone understand how these equations work? What we're now going to do is we're going to plug in. So we have Q metal, we're going to plug it in for Q metal. Q water, we're going to plug it in for Q water. And we get the following expression. So we have C metal. Let me use the red ink for that, just for consistency. C metal times M metal times T final minus T initial metal. Now, can we measure the mass of our metal? Can we measure the mass of our metal, and can we measure the temperature of our metal before and after we drop it into the water? Can we measure those quantities easily? Can we use the thermometer? Yeah, so these are easy to measure. Okay, let me just zoom out a short amount. So this is our expression for Q metal plus C water times M water times T final minus T initial water. And all of this entire expression is equal to 0. Now, our goal in this experiment, our goal in this first experiment is to solve for the specific heat of our metal. So we're going to do a little bit of algebra here, and we're essentially going to move this entire water term to the right-hand side and then divide by these two terms. And I'm going to spare you too much of the algebra, just so that way we can get to the main conclusion after rearrangement of this equation. We get the specific heat of our metal is equal to the specific heat of water times the mass of water times T final minus T initial times -1 divided by the mass of our metal times T final minus T initial metal. And we can measure the mass of water, the T final, the T initial of water. We can measure the T initial of our metal and the mass of our metal. So pay attention to all of the quantities that I've starred, as those are the ones that you'll be measuring in this experiment and measuring during the simulation. Does that make sense what we're measuring today? So just to be clear, we're going to mix our metal sample and our water sample. We're going to measure the initial temperature of our metal and water, and we're going to measure the mass of our metal and the mass of our water. After mixing, we're going to measure the final temperature and then plug each of those values into this equation. So that's part A. That's how we calculate the specific heat of a metal. Is everyone okay so far? Any questions before I move on to explaining part B? Okay, so let's talk through part B now. Let's talk through part B. So part B of the experiment, so in part B of the experiment, what we're going to be measuring is the heat of neutralization. So let's explain a little bit about what the heat of neutralization means. So we're going to be looking at the reaction between sodium hydroxide aqueous and hydrochloric acid aqueous to yield water and sodium chloride aqueous. Now this reaction does not just generate products, it also generates heat. So we can really say plus heat. And we can measure the heat of reaction and use that to quantify the amount of heat generated per mole that reacts. So let's draw up an analogy again. Let's draw up an analogy. So let's suppose we have a box containing some water. Let's suppose we have a box containing some water. And let's suppose the water is at 22 degrees Celsius. The way that I like to think of chemical reactions, is that I have a little box inside my water solution. So this is my reaction. And my reaction is going to generate and release heat or absorb heat from the surroundings. Okay? So then, by conservation, we know that the heat of reaction plus the heat absorbed or released by our water is going to be equal to 0. Energy is conserved. So the water is going to absorb heat from the reaction, or it's going to provide heat to the reaction in the event that the reaction absorbs heat. Does this equation make sense to everyone? The only thing that's new from our heat exchange equation is that instead of we're using the heat gained or lost by a metal block, we're using the heat gained or lost by our reaction. Now, we can quantify the heat absorbed or released by our water by expanding out this equation by noting that the Q water is equal to the mass of water times the specific heat of water times the T final minus T initial of our water. The same equation that we've used previously. So if we plug this all in, we get that the heat of reaction is equal to the mass of water times the specific heat of water times T final minus the T initial of water times -1. And don't forget this part, because remember, Q reaction is negative Q water if we're solving for the Q reaction. Now, let's do a run through really quickly of what's going on here. So let's suppose we have our solutions. So we have our HCl in water. We add that. Oops, one moment. One moment. Give me 1 second to get the Zoom sharing back up. One second, let me just reopen the OneNote tab really quickly. Let me reopen OneNote. Allow me 1 second. Okay, so let's continue on. So let's draw a picture of what's going on so that way everyone can help visualize and understand what we're measuring in this experiment. So we have our hydrochloric acid in water. We have our sodium hydroxide in water. And we are going to combine our two solutions together. So at the end of this process, we are going to have a mixture. We're going to have a mixture of our two solutions. And our two solutions are going to react and generate heat. So then, in terms of the mass that you're going to need to use, the mass of water is going to be equal to the total solution mass. So the total mass of both of the solutions you've combined together. The specific heat is going to be the solution specific heat, which is approximately that of water. And now, as the reaction proceeds, eventually we will be able to know the initial temperature of both of the solutions we mix. And at the end of our reaction, we will know the T final at the end of reaction. So we can measure our T initial and T final and plug them into this equation. Does that make sense so far? You're going to mix the solutions together, record their initial temperature and the mass of each solution added. The total mass of each of your solutions is the mass that you're going to plug into this heat equation. The specific heat is the solution specific heat, which is almost identical to that of water. The T initial is the initial temperature before reaction, and the T final is the temperature at the end of the reaction. Does that make sense so far? Let me open up chat. Are there any questions? Okay. Perfect. So I see a lot of, oh, whoops. One moment. Let me just reopen OneNote. Okay, so continuing on from here, one little catch, one little caveat to this method is that we will not be able to measure T final directly. Instead, if we take a look at what's going on in our calorimeter or in our reaction vessel, we'll notice that we have to account for one other effect before we can report T final. So we have our metal sample, so we have our reaction in water. And our reaction is going to both exchange heat with the water and it's going to exchange heat with the surroundings. So the key point of this picture is heat is lost to the surroundings. So in order to get around this problem, in order to get around this heat loss issue, we will instead graphically determine T final assuming an instantaneous reaction. So let's look at what's going to happen as our reaction proceeds. So if we monitor a reaction carefully, we'll have a plot of temperature versus time in seconds. So in this neutralization reaction, initially we'll start at around 21 degrees Celsius. And then as the reaction begins, our temperature will climb and climb and climb. So this is during the reaction. And then over time, eventually our temperature will peak and then slowly decline. So the key time point that you want to note is the temperature when you, is the time when you begin to mix your sample. We're going to call this T mix, which is T is equal to 0. Now, when you plot temperature versus time, you're going to end up with a bunch of data points as your temperature rises, and then a bunch of data points as your temperature falls. What you're going to do is you're going to take your data points after your maximum temperature, and you're going to fit a line of the form y equals mx plus b. So you're going to make a linear fit of only these data points. And what you're going to do is you're going to take that fit and you're going to extrapolate to T is equal to 0 or T mix. So for example, suppose you get an equation, so the Y in this case is the temperature equals M, so M is your slope. X is your time, and B is your intercept. And essentially what you're going to plug in is you're going to plug in X is equal to 0, and you're going to write down the Y value. So the Y at T equals 0, which is T mix, is going to be your T final. So this temperature right here is going to be your T final. and you're going to read the temperature from the graph. Does that make sense how we're going to graphically determine T final? So just to reiterate once again, what you're doing. You're going to collect on your own the temperature as a function of time. So for example, every 5 seconds, you're going to write down the temperature. You're going to plot that graph of temperature versus time. You're going to note the time when you mixed your samples. T mix will be T equals 0 on your graph. Then, once you notice your temperature declining, or once you notice you're past your peak temperature, you're going to plot the data points after the peak and fit a linear fit of y equals mx plus b. Once you have the linear fit in place, you're going to plug in for time equals 0, which is x is equal to 0, and the temperature at time is equal to 0 is your temperature of instantaneous mixing, T final. So this is the temperature assuming no heat was lost to the surroundings and that the reaction exchanged its heat instantaneously. Now, this is important to note. This can only be obtained graphically because the temperature we experimentally measure is the temperature that includes heat loss to the surrounding. So the temperature that we measure directly is not necessarily fully reflective of the actual heat generated from the reaction because some of that heat is lost. Is everyone clear on what data we're collecting and how we process the data to get T final? Does anyone have any questions at this time? Anyone have any questions? So once you get the T final, again, we know that Q reaction is equal to the mass of the reaction solution times the specific heat of the solution times the T final minus T initial times -1. And then we can calculate what is known as delta H, which is the enthalpy, by taking the Q reaction over the moles of limiting reactant. And in this experiment, I'll tell you that our limiting reactant is going to be sodium hydroxide. So you're going to take the heat of reaction and divide it by the moles of sodium hydroxide that reacted. And this gives us a standardized way of describing how much heat is generated per mole of chemical species that reacts. And this is the value that you're going to report. It should be about -55 kilojoules if you calculate everything correctly. Does that make sense so far? Is everyone comfortable with part B? Everyone's pretty silent. If you could just chat to let me know. Yes, yes, you'll attach it as a file in Canvas. The main thing is they're able to get the T final from your graph, as that's what I'll be looking for. I won't be too picky about the exact structure of your graph, as long as it's adequately labeled and your fit is done properly. Any other questions on the calculations for this portion of the experiment? If not, let's talk about part C. So part C is pretty easy. It's the enthalpy of neutralization. Enthalpy of solution. So in the enthalpy of solution, so if we look at, for example, ammonium nitrate solid, and we try to dissolve it in water. So we're going from ammonium nitrate solid to ammonium nitrate aqueous. So in this process, we know ammonium nitrate happens to be a major component of cold packs. And we know that when you crush a cold pack, the cold pack instantly, the water inside the cold pack decreases in temperature. So this process, as ammonium nitrate dissolves, this process absorbs heat. The delta H is greater than 0. So we're going to measure the enthalpy of solution for a range of compounds. And the way that we're going to do that is we're going to take a sample of water. At a temperature initial, T initial. We're then going to take a sample of solid. So in this case, let's suppose we have solid ammonium nitrate. And we're going to measure the mass of the solid. And we are going to mix the solid into our water. Now, just like our example with our chemical reaction, this physical process, is going to absorb heat. I always like to draw a box to help me visualize heat transfer. So this physical process will absorb heat. Okay, so we're going to have a solution. So we're going to have a solution so we can record the mass of the solution and the T final of our solution. Now, just like before, some heat is exchanged with the surroundings. So what we're going to do, just like before, is we are going to record the temperature as a function of time. And then we're going to use that data to make a plot of temperature versus time in seconds. Now, suppose initially our temperature, our T initial, is about 22 degrees Celsius. If I told you that this physical process, that when we dissolve ammonium nitrate, it absorbs heat, what will happen to our temperature of our water? Just think of crushing a cold pack. What happens to the temperature of the water in the cold pack? Does it increase or decrease? What happens to the temperature of water in a cold pack? It decreases, right? Exactly. So our temperature is going to drop and then rise again. Sorry, let me show that a little more clearly. Now, what you're going to do is you're going to plot the data points after the lowest possible temperature, the lowest observed temperature, and then you're going to make a linear fit. So y is equal to mx plus b, just like before. And we're going to extrapolate to t mix, which is time is equal to 0. So we're going to plug in x is equal to 0 into our linear fit, and that will give us the temperature at T mix. So after extrapolation, this temperature would be T final. So the reason why the temperature decreases is because the dissolving process absorbs heat. So as it's absorbing heat from our water, as our water loses heat, the temperature of our water will drop. It's the exact opposite of our example for neutralization, where the reaction releases heat, and as a result, the water increases in temperature. Does that make sense? Okay, perfect. Any other questions on the graphical format? Any other questions on calculating T final? Now, let's dissect just the energetics of this process. So we know that the Q of solution plus the Q absorbed or released by our water. Let me rename this. The Q, I'm going to call this Q dissolving plus the Q of our solution, any heat released by our solution, and any heat absorbed by our dissolving process must be equal to 0. We can solve for the Q dissolving, and that in turn gives us -1 times the heat released by our solution. Now, let's really focus on what components do we have in our solution? What two things do we have in our solution? If we take a look at this picture, what two things do we have in this solution mixture? What two things do we have? And feel free to type in chat. There are two things that we have in our solution. What two things do we have? Yep, exactly right. The solid and the water. So for Q dissolving, it's going to be equal to -1 times Q solid plus Q water. And now expanding our equation, the Q dissolving is going to be equal to -1 times the mass of solid times the specific heat of solid times T final minus T initial plus the mass of water times the specific heat of water times T final minus T initial. There we go. So we're accounting for the heat released from both our water and our solid during this dissolving process. And we've measured T initial, and we will measure T final graphically, and we will be able to, from our simulations, to record the mass of each of our components, and the specific heat of our solid and water are given in your lab manual. So we have all the data we need to calculate the heat absorbed when we dissolve our ammonium nitrate. Oops. Now we can go a little bit further here, and we can calculate the delta H for this dissolving process by taking the Q, the heat absorbed as our solution dissolves, and divide it by the moles of solid dissolved. And this gives us a measure of the amount of heat absorbed as we dissolve our solid. Does that calculation make sense to everyone? So this is the entirety of the lab. Does anyone have any questions? I'm just going to do a quick run through of the entire theory once again, just to help everyone get everything in order. So let's talk about what we've established. Let's talk about what we've established so far. So from our baseline, heat is exchanged from high temperature objects to low temperature objects in thermal contact. They will exchange heat until they're at the same temperature. We know from the first law of thermodynamics, energy is conserved. Any heat gained by our water is lost by our metal. So we can relate the heat absorbed by our water and the heat lost by our metal. You'll be doing the virtual labs on your own, though you're welcome to work through them in groups. I would recommend attempting the simulation during the lab time as well. Continuing on with our overview, we can describe how readily an object changes temperature as it gains or loses heat using the heat capacity and specific heat. So the specific heat, CS, has the units of joule per gram degree Celsius, energy per gram degree Celsius, and it describes the energy required to raise the temperature of 1 gram of material by 1 degree Celsius. So objects with large specific heat capacities in turn require more energy to raise their temperature. Now, The reason why this is so useful, is that the specific heat provides a relationship between the heat gained or released by an object and the temperature change experienced by that object. So then, for example, in part A, when we dump our metal block into our water, our goal in this experiment is, for part A, is to measure the specific heat of our metal. So in order to do that, we're going to measure the mass of our metal, the initial temperature of our metal, the mass of our water, and the initial temperature of our water. Now, once we allow the metal and water to sit, they'll eventually exchange heat and reach the same temperature, T final. So we'll write down the final temperature. We know mathematically that any heat released by our metal was gained by our water. So in turn, when we substitute our expressions for heat using our specific heat capacity and temperature, we can solve this expression and calculate in turn the specific heat of our metal by measuring the mass of each of our components, the initial temperature of each of our components, and the final temperature. Everyone following so far? Does this make a little more sense when I'm reviewing it one more time? Any questions so far? Okay, let's keep going through this run through then. In part B, we're measuring the heat of neutralization. It's the heat produced by a reaction of sodium hydroxide and hydrochloric acid. I like to think of it as my reaction's a little box that's releasing heat into my solution. So we know that any heat gained by our reaction or any heat released by our reaction will go into our water. So any heat released by our reaction is absorbed by our water. We can write expressions for the heat absorbed by our water by measuring the mass of the water, specific heat of the water, and the change in temperature. So we can plug that in to our expression for the heat of our reaction. And in turn, one thing that you do want to keep in mind is that the mass that you're using should be the total solution mass of both of the solutions mixed together. And we'll determine the T initial will be given from the simulation, and T final you're going to calculate graphically. So heat is lost to the surroundings. So you're going to plot temperature as a function of time, and you're going to plot the data points after the temperature begins to drop from the peak and fit it to a linear fit. Then you're going to plug in and extrapolate to T mix, which is time is 0. And once you have your data, if you're working on the graphs, I'm more than welcome to help and look over your graphs. Once you have the T final from your graph, you're just going to plug it in to your equation for the heat of reaction. Finally, you'll calculate the enthalpy, which is the heat of reaction per mole of material, by taking the heat of reaction over the moles of sodium hydroxide that react. Finally, for part C, we're going to be measuring the enthalpy of solution, which is the heat absorbed or released when a substance dissolves. So we're going to record the mass of our solid and the mass of water and the initial temperature of both our solid and our water. When we drop the solid into the water, we're going to then measure the temperature as a function of time, and graphically our temperature will drop, and then we're going to plot all of our data points after our temperature begins to rise, and we'll fit it to a linear fit of y equals mx plus b. This is temperature as a function of time. We're then going to extrapolate the plot to T mix by plugging in x is equal to 0 or time is equal to 0. And from that, we'll get the T final, assuming instantaneous reaction and no heat loss to the surroundings. Just like before, we can use our conservation of energy and heat exchange equations to solve for the heat associated with dissolving our solid. The only thing that's new in this case is that we are using the heat released by both our solid and our water. And all of these values we'll be measuring in this experiment. We'll be measuring the initial and final temperature, and we'll be measuring the mass of water and our solid. The specific heats of our water and our solid are given in the lab manual. Once you have the heat associated with dissolving your sample, you're going to calculate the enthalpy of solution by taking the heat associated with dissolving your sample and divide it by the moles of solid dissolved. And that's our review of today's experiment procedure. Are there any other questions? I want to make sure everyone has enough time to work through their simulations. So what I was planning for the next hour and a half is I'll let everyone go through and try to work on the simulations. You don't have to get them all done today, but if you have any questions, now would be a time if you can send them in chat or send me a message via Canvas, and I'll be more than happy to address your questions. Anyone have any questions or last minute comments? Is everyone okay with being let loose to view the simulations? Please make sure you're muted when you're viewing the videos, just so that way we don't have 19 videos going on in the background. But beyond that, that's all I have for the pre-lab lecture, and you're welcome to get started with the simulations, and I'll be here to answer your questions. The lab session will be open until our end time of 5:25. Yep. Mm-hmm. And I'll be checking the chat periodically while everyone works through the simulations. Well, if there aren't any other questions, I'm going to mute my video and audio and pause the recording.